Hello students, so let us continue. Let us start with the polarization of ions or covalent character. Covalent character in an ionic bond. Covalent character of ionic bonds. So first point you can remember there are 100% ionic and 100% covalent character is not there. An ionic bond always associated with some covalent character as well as a covalent bond is associated with some percentage of ionic character as well. You can say one is higher, one is lower like that. Why so? Let us check. First we can discuss the covalent character of an ionic bond. Let us start with the simplest example. We know sodium chloride is more ionic, right? But now it is observed that in an ionic bond it existing as Na plus ion and Cl minus ion, that is cation and anion. It is observed that the positively charged cation, let me represent like this, a positively charged cation have the ability to distort the electron cloud. Let me represent, this is chlorine minus and there will be electron cloud will be there around the chlorine ion. And it is observed that a positively charged cation has the ability to distort the electron cloud. You imagine electron cloud are there around the chloride ion. So it is observed that the chloride ion will disturb the electron cloud, and this cation will disturb the electron cloud, or no, the electron cloud are slightly attracted towards the positively charged ion. It is no, it's a ability of this cation which is to attract the electron cloud of this anion, or we will say no, polarization of anion, or no, distort the electron cloud of anion, so that no, some electrons are coming towards the cation, which means no, you will see the electron cloud are more often in between the cation and anion. That means electron cloud in between two species means that is covalent nature. That's a covalent behavior. Hence it is observed that a cation has the ability to distort the electron cloud of an anion, thus developing a covalent character. This is what we are discussing here. So which type of cation will distort? What's the nature of anion? That we can discuss. This theory is developed by Fajans. Hence this rule we will call Fajans rule. So Fajans rule will tell you the rules related to the polarization of anion, or the polarizing power of cation. There are two species, two things is happening. One, cation polarizes the anion. The cation which will distort the electron cloud of anion, and what's anion in the case, they get distorted. So polarization of anion, this is the two main things that are happening in when in an ionic compound. So let us discuss Fajans rule. First rule, the first point related to Fajans rules, polarizing power of a cation. The polarizing power of a cation is proportional to polarizing power of cation is proportional to, always proportional to, smaller the ion. If the size of the cation is smaller, then polarizing power is greater. Smaller the size of cation, smaller the size of cation, greater the polarizing power. Let us have an example. If you fix the anion, it is observed that among lithium chloride, sodium chloride, potassium chloride, and cesium chloride, so rubidium chloride, and cesium chloride. So this is the increasing order of cation, right? Lithium smallest, then followed by sodium, potassium, rubidium, cesium. Anion, we are fixed anion having a charge that is anion is chloride ion. So it is observed that the covalent character is greater for lithium chloride compared to sodium chloride, potassium chloride, rubidium chloride, and cesium chloride. That means here only we have a comparison between size of cation. The size of cation is smallest for lithium, highest for cesium ion. So lithium chloride having the smallest cation has the highest ability to distort the electron cloud or highest polarizing power. So smaller the size of the cation, higher the polarizing power, higher the covalent character. Remember, ionic character is just the reverse. If the covalent character is higher, means no, ionic character will be less. That's the way no it will go. It is just opposite to each other. So that's the first point related to the Fajans rule, polarizing power of a cation. Second point, what about anion? If the size of the anion is higher, size of anion is higher, size of anion is higher means no, higher the polarizing power. Talk about polarizing power again, no, here not polarizing power, it's a polarizability, how much no anion is getting distorted. If that's observed that no, if the anion size is higher, then no, the polarizability or no, the percentage of covalent character, we can say the degree of covalent character actually increases with the size of anion. This is again no, reason is if the anion size is higher means no, the electron cloud are much more further away from the nucleus, which means no, outer electron experience less nuclear attraction, which means no, the outer electron are can be easily distorted by a cation. So that's the way you can imagine. Size of the anion higher means no, the inner electron will be there. Inner electron also have a shielding effect, which means outer electron experience less nuclear attraction, which means a cation can easily distort an anion. So higher the size of the anion, greater is the covalent character. That's the second point. Similarly here now you can imagine smaller the size of cation means no, nucleus have much more effect on the no, the for the distorting power. So that always the case. The smaller the size of cation, higher the size of anion, greater the covalent character. The third point related to the charge of the cation. Larger the charge, higher the charge, larger the charge of cation, higher the covalent character. So it is observed that among this no, Na plus NaCl, MgCl2, AlCl3, it is observed that NaCl having the least covalent character compared to MgCl2 and AlCl3, because Na plus charge, Mg plus 2, Al plus 3. Higher the charge of the cation, higher the covalent nature, which means no, it has charge of the nucleus is higher, which means no, greater polarizing power. That's the way no, charge of cation is related. Similarly, another point that you can remember is it is observed that transition metal cation having the higher polarizing power compared to this no, non-transition metal cation like alkali metal cation, alkaline earth metal cation. So transition metal cation having higher polarizing power compared to a non-transition metal cation like alkali metal ion, alkaline earth metal ion, because there no, you will see in transition metal ions no, d orbitals and f orbital electrons are coming, which means they generally have a poor shielding effect, which means outer electron experience no, high nuclear attraction. So that's the case where no, inner electrons are poorly shielding means no, cations no, have that more influence on the outer electrons. So cations which no, in the case of transition metal ions, inner electrons no, and generally no, d and f orbital which are poorly shielding. So nucleus have more effect on the polarizing power. Polarizing power will be greater for a transition metal cation. Where no, non-transition metals is the reverse the case, where generally no, once losing an electron, cation become a noble gas configuration. So they have no, generally s and p orbital which have no, better shielding effect. So the nuclear effect will be less, because no inner electron shields the nuclear charge. That means no, if you compare a transition metal cation and a non-transition metal cation, it is observed that no a pseudo noble gas configuration like transition metal cations having a more polarizing power compared to a non-transition metal cation. This is again how much no nuclear attraction that it can have on the anion. So that's the way you can have comparison related to Fajans rule. So Fajans rule tells you that yes, in an ionic bond there is a covalent character is there. That covalent character always no related to these four factors. So that's all for the covalent character in an ionic bond. Now just think the reverse case where no ionic character in a covalent bond. Will it possible? Yes. Ionic character. Ionic character in a covalent bond. Ionic character in a covalent bond. So this is the case where now you think a covalent bond and how much ionic nature is developed. This is now especially related to the electronegativity difference between the two atoms. So consider a simple covalently bonded two atom. Here I am taking hydrogen molecule. In hydrogen molecule you can see two hydrogen atoms are attracted by a pair of electron. Here one electron coming from this hydrogen, one electron coming from this hydrogen. So this is the case where no a pair of electron which is now attracted by these two atoms. It is observed that now both the atoms are same, they have similar electronegativity, which means no both attract the shared pair of electron equally. Hence now we can say this is non-polar in nature. Non-polar in nature. There is no real electronegativity difference between the two atoms. Hence no there is no real shifting of electron towards one atom. This you will understand if you consider other case. Look at HF. Here now the point is different. Here both are covalently bond. This is a covalent bond where one electron coming from this hydrogen, one electron coming from this fluorine. But it's observed that this pair of electron is more towards the fluorine atom because fluorine is more electronegative. So it has the ability to attract the shared pair of electron more towards itself, which means a partial negative charge will be developed on fluorine, partial positive charge will be developed on the hydrogen atom, which means partial, not complete. Not complete transfer of electron takes place, but no a great extent of attraction from the more electronegative atom. So we will say a dipole, there is a dipole is developing where one is positive charge, other is negatively charged. Remember, it's only partial. But now we will say a polarity will be developed to, in a direction where now we will represent like this, where fluorine is more electronegative. So it will pointing towards the more electronegative atom. So this is the way you can represent the polarity. So which means HF is polar because of the more electronegative nature of fluorine, and hydrogen molecule which is non-polar because no both are same atom, they have similar electronegativity, so they attract the shared pair of electron equally, which means more often you can expect the electron pair at the center where there is no real shifting of electron pair from one atom to other atom takes place. So that's the case. Now you can understand ionic character developing. Ionic character here means no a positive and negative charge develops. A positive and negative charge develops in a covalent bond. So now let us think another case where now in an H2O molecule, H2O molecule having a bend shape. So this is the case where no you can understand oxygen more electronegative. So oxygen is more electronegative means no the polarity will be more towards the oxygen atom because in the OH bond oxygen is more electronegative, so polarity will be towards the oxygen atom. And here also you can see in the OH bond, oxygen is more electronegative, so polarity will be in this direction. Remember, no, when you talk about polarity, we actually measure in terms of dipole moment. That I will tell you what it is. Here you can see the polarity will be in this direction. Here polarity will be in this direction, and there is a lone pair of electron as well in oxygen, which is acting in the upward direction. Remember, this is a vector quantity. Polarity is a vector quantity. So you have to know to find the dipole moment of a molecule. No, you have to consider the vector sum, resultant vector sum. Where this is in this direction, this is in this direction. So and lone pair is also there. So you will see a resultant dipole moment in the upward direction. So definitely water is polar. No, polarity we can measure in terms of dipole moment. That I will tell you. One more point: if you compare this hydrogen halides HF, HCl, HBr and HI. Among this, it is observed that hydrogen fluoride is it is more polar compared to HCl and compared to HBr compared to HI, because fluorine is more electronegative compared to chlorine, bromine, iodine, hence polarity will be higher for HI. So HF. That's the case. Now you can remember related to the electronegativity, where fluorine is most electronegative, so polarity will be higher. Okay, this is the case where heteronuclear atom forming a so the two atom which is heteronuclear in nature, right? Both are different atom, so there is a dipole moment will be there in the direction of electronegative atom. So that's the case with the a heteronuclear atom. If it is a homonuclear atom like fluorine, chlorine. Now this is the case where both are same atom. Even though fluorine is electronegative, you understand. If both are same means they attract the shared number of electron equally, which means fluorine molecule have dipole moment. Polarity will be zero. Dipole moment will be zero because both are same atom. They attract the electron pair equally. So let us have a measurement. How can you measure the dipole moments? You can measure dipole moment by using you can measure polarity by dipole moments. That's the case. Now how can you measure? You consider two atoms. One is having a partial positive charge, other having a partial negative charge. The partial negative charge means it is more electronegative atom. So dipole moment means you can represent this by mu, which is the charge at one center, which is we represent as q, and distance between the dipole. Distance between the dipole distance between the dipole we represent as r. So if B is more electronegative means the polarity will be towards the B direction. So this is the way you can measure the dipole moment. Mu is equal to QR, where mu is the dipole moment, Q is the charge at one center, which means one atom, the magnitude of charge, one atom gains more charge, other atom gains less charge. So you can consider magnitude of charge at one center and distance between the dipoles. So the unit will be coulometer. You can express the dipole moment in coulometer. Coulomb is the charge, unit of charge, and m is the distance between the dipole means we are expressing in meter. So coulometer or not dBA, or you can represent in dBA, where 1 dBA which is equal to, you can remember this value, that is equal to 3.33564. 3.33564 into 10 raised to minus 30. 10 raised to minus 30 coulometer. So either you can express in dBA or you can express in dBA or coulometer. So let us have value. Consider a dipole, which is you imagine the charge at one center is developed due to the charge of electron. So charge of electron is 1.0622 into 10 raised to minus 19 into the distance between the dipole, let it be 10. Let it be 10 into 10 raised to minus 10 meter, or we can say 10 distance between the charges 10 raised to minus 10 meter, 10 raised to minus 10 meter, or equal to 1 angstrom. So if you know calculate the dipole moment, which is with charge at one center into distance between the center. So if you calculate it, you will get 1.6022 into 10 raised to minus 29 kilometer, right? So this we can convert it into d by dividing by 1 dB is equal to 3.33564 into 10 raised to minus 30. So if you calculate it, you will get around 4.803 dB. Okay, so this is the way you can find mu, the charge at one center into distance between the dipole. If you want to convert it into dB, divided by 1 dB, divided by 3.33564 into 10 raised to minus 30. So that's the way you can measure the polarity. Okay. Now think percentage of ionic character. What is the percentage of ionic character? We know there is ionic character will be there in a covalent bond. How can you measure? The percentage of ionic character will be equal to, we can have an equation for that, mu observed ionic character divided by mu ionic into 100. This is the case, mu ionic means, you imagine a complete transfer of electron. If a complete transfer of electron takes place, that is the maximum ionic character. If in covalent nature, if you talk about covalent nature and ionic bond in polarity, there is a partial charge will be developed. There is no real complete transfer of electron takes place. Keep that in mind. So here now polarity means electron cloud distortion only. So here having this equation, mu observed divided by mu ionic into 100 will give you percentage of ionic character. Let us do one problem for that. The measured dipole moment of HCl, that means it's observed dipole moment, that they will give, that is observed 3.57 into 10 raised to minus 30 kilometer. That's observed dipole moment. And this is, now how can you find the mu ionic? Mu ionic you can find by you imagine a complete transfer of electron takes place, means the charge will be exactly equal to the charge of electron, 1.602 into 10 raised to minus 19 coulomb into the distance between the dipole, that they will give, that is equal to 1.275 into 10 raised to minus 10 meter. That's the distance between the two ions, or they given bond length. Bond length is the in an ionic bond we know it is cation and anion will be there. The distance between the cation and anion will be the bond length. So bond distance they given. So that is actually equal to 1.275 into 10 raised to minus 10. If you calculate it, you will get mu ionic, which will be exactly equal to 2.043 into 10 raised to minus 29 kilometer. So we have this observed dipole moment that they will give, and observed ionic will have. So divide this 3.57 into 10 raised to minus 30 divided by 2.043 into 10 raised to minus 29 into 100 will give you the percentage of ionic character, which is, if you calculate it, you will get 17.47 percentage. That means HCl is not that much ionic. It is it's more covalent in nature. The ionic character is less, we have to say. It's only 17.47. So HCl is more covalent in nature. So how can you find the percentage of ionic character? mu observed divided by mu ionic into 100, where mu observed, now it's observed dipole moment divided by mu ionic. This is now we expecting a complete transfer of electron to take place. What is the maximum ionic nature? So if one electron is transferred means no, the charge will be 1.6022 into 10 raised to minus 19 coulomb, and the distance between the cation and anion, that's no bond length for you, that is equal to 1.27 into 10 raised to minus 10 meter. That's given. Multiply that, you will get mu ionic. So mu observed divided by mu ionic into 100 will give you the percentage of ionic character. So that's the way you can find the what is the percentage of ionic character. Now let us think dipole moment and dipole moment of different structure. Let us have a discussion of that. Now shape of the molecule is very important to decide the dipole moment. Now we can find the resultant dipole moment. You can find it using the equation mu, which is equal to root of mu1 square plus root of mu2 square plus 2 mu1 mu2 cos theta. This is the equation that you can use to find the resultant dipole moment, because now you think H2O molecule. Here no dipole moment will be acting in this direction, let it be mu1. Here dipole moment is acting in this direction, let it be mu2. So what is the resultant dipole moment? That you can calculate mathematically using this equation. Root of mu1 square plus mu2 square plus 2 mu1 mu2 cos theta, where theta is the angle between two dipoles. So that more often equal to the bond angle as well. So having this equation, you can find the resultant dipole moment. Okay, let's keep in that mind. Then let us discuss some structures. Beryllium fluoride. Beryllium fluoride have a linear structure. That's something that you have to learn from BSCPR theory. Here fluorine is more electronegative, so its dipole moment will be in this direction. Here dipole moment will be in this direction because fluorine is more electronegative. Interesting fact, both in opposite direction, dipole moment will cancel, which means mu is equal to 0. The net dipole moment for beryllium fluoride is 0, because even though there is electronegative atom, fluorine is there, dipole moment found to be 0. Similar is the case with the CO2. Carbon dioxide having a dipole moment which is equal to 0, because oxygen is electronegative and more electronegative than carbon, but since it have a linear shape, dipole moment cancels each other, so net dipole moment will be 0. In the case of water, we have a net dipole moment which is equal to 1.84 d by. You can keep that in mind. Water is having a dipole moment which is equal to 1.84 d by. Now let us think two interesting cases with NH3 and NF3. Both NH3 and NF3 have a pyramidal shape. Keep that in mind. It having a pyramidal shape with one lone pair of electron in on nitrogen. NF3 similarly. Now a student can easily think in terms of dipole moment. A student can easily think fluorine is more electronegative than definitely hydrogen. So fluorine is more electronegative than nitrogen, and here nitrogen, if you compare electronegativity between nitrogen and hydrogen, a student can think nitrogen is more electronegative. Here NF3 more fluorine is the highest electronegative atom. So normally a student will think this have a higher dipole moment, but it's not so, because here think in terms of direction of dipole moment. Here hydrogen is less electronegative, so dipole moment will be in this direction. Here also dipole moment will be in this direction. Here also dipole moment will be in this direction, and here a lone pair of electron is there, so that also you have to keep in mind, that in the upward direction. So there will be a net dipole moment in the same direction. There is no real mutual cancellation of dipole moment takes place. But it's not the case with the NF3, even though they have pyramidal shape. Here dipole moment will be towards the fluorine, here also towards the fluorine, here also towards the fluorine, but here now a lone pair of electron is there that acting in the upward direction. So you will see the net dipole moment is there, not fully cancelling. Here you can see some dipole moment is there because of this, and also a net dipole moment between dipole moment between, because of these two. So yes, there is some some dipole moment, net dipole moment is there towards this direction, but still some cancellation is there because of the lone pair of electron. That means N of 3 is less polar compared to NS3. Let us have a value. Dipole moment is equal to 1.49 dBA for ammonia, while it is 0.24 only, 0.24 dBA for NF3. So when you ask such question, it's very important to draw the structure and explain through the structure. Talk about no methane. Methane, no, it's having a non-planar structure. It's not a planar structure. So CH4 methane having a tetrahedral structure, where now you have to remember one atom which is coming towards you, that's represented by thick line, and one atom going away from you, that's represented by dashed line, and two atom which is in the plane. 2 point you can remember electronegativity between carbon and hydrogen is very less, which means no more often you will see CH4 is no CH4 will be dipole moment will be 0, but now in CCl4 also you will observe its dipole moment will be 0. CCl4. I'm talking about no carbon tetrachloride and CH4. Both CH4 and CCl4, the dipole moment will be 0. So this is the case where now it having a non-planar structure, and now one atom which is going away from you, one atom coming towards you, there is a mutual cancellation of polarity takes place. Similarly, the atom which is in the plane also cancels each other. So there is a dipole moment cancelling each other takes place if the both the four atom in a tetrahedral carbon, if that is same, dipole moment will be 0. That's you can understand through CH4 and CCl4 having a dipole moment 0. But it's not the case with CHCl4, CHCl3, where now one you can imagine one hydrogen atom, two hydrogen atom, and 3 hydrogen atom, one which is no, one is different, CHCl3 I am talking about, sorry, CH3Cl, both now having a dipole moment. So CH3Cl, here you can see a dipole moment is there now towards the fluorine direction, where fluorine is more electronegative. There is no real cancellation of dipole moment takes place in CH3Cl. That means CH3Cl having a dipole moment which is equal to 1.84 dBA, while dipole moment is 0 for CH4 and CCl4. So dipole moment definitely influence the electronegativity difference between the two atoms, but it's more important you have to think, no, it is the most important point that I believe the direction as well, because no vector is a vector quantity, dipole moment is a vector quantity, so you have to think about the direction of dipole moment when you talks about this, no, when it talks about this dipole moment. Now let us discuss to the final point how to measure what's application of dipole moment. First application of dipole moment will be you can have the bond angle. What's the bond angle? In a covalently bonded molecule, you can have a bond angle if it is polar using the equation that we already told, mu. Let us think about mu H2O. How can you find the dipole moment? Mu H2O is equal to mu OH, both are same, so mu OH square plus mu OH square plus 2 mu OH into mu OH into cos theta. So having this equation, you can calculate the bond angle, because no theta will give you the bond angle. So if mu H2O, that's given 6.14 into 10 raised to minus 30, that is the dipole moment value, and mu OH dipole moment, that you can mu OH square plus mu OH square is equal to 2 mu OH square. If you take that is outside. Here, if you take outside, you will get into 1 plus cos theta. You can take that outside to mu h square, you can take outside into 1 plus cos theta will give you the resultant dipole moment. So here now you can square it so that now this root will be gone. So we have 6.14 into 10 raised to minus 30 whole square, which is equal to 2 into mu h that they will give you. That's here is given 5 into 5.02 into 10 raised to minus 30. 5.02 into 10 raised to minus 30 square into 1 plus cos theta. So you can find cos theta, this divided by this minus 1. So you can do this divided by this minus 1, which is equal to 6.14 into 10 raised to minus 30 whole square divided by 2 into 5.02 into 10 raised to minus 30 whole square. If you minus 1, if you do this, you will get theta cos theta. From there cos inverse, if you take, you will get theta as well. So theta you will get around 104.104 degree, 104 degree and 36 minutes. So this is the angle that you will get, nearly equal to the actual bond angle, 104.5. So definitely dipole moment measurement will give an idea about the between the bond angles between two dipoles. That's another application of dipole moment. You can find the bond angles. Second point, now you can understand between cis and trans compound. For example, a compound like this, where I will say this is cis because same atom on the same side. So cis 1,2 dichloro ethene. This is the case where now I will say dipole moment will be greater than 0. That's one way you can distinguish between a cis and trans. Where trans, now you will see dipole moment will be 0 because dipole moment cancels each other. Look at this, here dipole moment acting is this direction, here dipole moment acting is this direction, mutually cancels each other, which means dipole moment will be 0 for a trans compound. So that's the way you can distinguish cis and trans compound having a dipole moment equal to 0 while cis having a net dipole moment. Similarly, you can understand between para and ortho meta para products in a aromatic compound. For example, understand 1,4-dichlorobenzene. Look at this. Here, dipole moment will be 0 because dipole moment acting in opposite direction, so it will be 0. Not the case with ortho and meta. They have a net dipole moments. They are having a net dipole moments. So no, it won't be 0, not equal to 0. Similarly, in the case of meta, you will see there will be a dipole moments which having greater than 0 value. So that suggests you can distinguish between ortho, meta and para products. Ortho meta from para product, where para product having a dipole moment is equal to 0, where ortho meta having a net dipole moments. So that is the three important application of dipole moments. So please go through the portions, which is very important. Especially when you talk about polarity, which is coming in the organics as well. So try to understand things. It's very important to learn the structure of the molecules to have the direction correctly. So thanks for listening. Let us wind up. Thank you.